Check one. Can you all hear me in the YouTube? Can you all hear me on YouTube? You can send a message. Okay, great. Perfect. Right. Good evening, everybody. We'll start off after about 2 weeks of break. We've started back again. There were some technical issues to be sorted out, so now it's all done. So we'll start off with some MCQs from your circular and rotational motion. Okay? Circular and rotational motion. Page 21, question 21. So rotational motion. These are some doubts which you have sent me. Rotational motion. One end of a thin elastic string length L attached to a small object of mass M resting on a frictionless horizontal surface, and the other end is fixed to a point on the surface of a vertical cylindrical pillar of radius r, so that the string remains horizontal. A velocity v is given to the object perpendicular to the string and along the surface as shown in the figure. The angular velocity of the object around the axis of the pillar when it hits the pillar. So if you look at this carefully, here you have the cylinder. Here you have the cylinder. Question 21. Now, there is a string connected here tangentially. String and mass connected. String and mass connected. And this is traveling tangentially like that. So it's going to wrap around. The best thing is I'll look from top. Huh? When I look from top, how will I see it? So this is how I'll see it. You will see the string will wrap around and collide directed towards the center. So what will happen here is very simple and direct. The object will rotate around and come and knock directed towards the center. Tell me now. If it's directed towards the center, will you have an angular velocity? No. No angular velocity, right? Technically, there is no tangential velocity. It's directed towards the center. So your angular velocity is going to be how much? 0. Angular velocity is 0. Okay. Angular velocity is 0. Then question number 30. This what do you call? We call this Babara Chakra. The Babara Chakra question. So here it's like this. Majority of the questions, I think they have given it here. I mean, whatever you need to think, they have given it. A circular disc shape pinwheel type framework firework shown in the figure performs rotation about the Z axis. It's rotating about the Z means vertical axis. A constant reaction force is generated by its burning. Constant reaction force. So due to burning, there's going to be a push which occurs. I'll mark this. There's a force which occurs that way, which creates a torque. A force which occurs, which will create a torque. The radius to the center here is R. They're telling you the force is constant. Nah? So here this force is constant. Don't forget the force is constant. Right. So you can underline those keywords. Force is constant. Moment of inertia is half mr squared. So when the radius is changing also, the torque or the force remains the same. Okay. Right. Mr omega alpha mass radius angular velocity angular acceleration. What can you say about this? So if I look at it, torque equal I alpha. So torque is given by this constant burning force. So torque is R times F, moment of inertia, half mr squared. There you go, alpha. Now you can cancel off R and R. R and R you can cancel off. F is equal to half mr alpha. Now they are telling you force is a constant. So 2F anyway will be a constant. This part anyway will be a constant. So mr alpha will remain constant. Mr alpha constant means answer is answer number 1. Mr alpha is constant means answer is answer number 1. Right. Question number 70. Question number 70. These are small ideas, but important when it comes to MCQ. Question number 70. Carefully look. Question 70. Read that. A figure shows a bicycle wheel which is rotating with a large velocity omega about the axle. AB hang from the string. So the famous experiment. I will send you all a video on this. We have this rotating here. And let's say you are rotating it in that direction. There you go. You make it rotate in that direction. Right. Don't forget, the weight of the wheel is also here. The weight of the wheel is also here. The weight of the wheel is also here. This distance is R. Right. Now there will be a torque. Right hand grip rule. RMG torque will be in that direction along the axis of rotation. RMG torque will be into the board. RMG torque will be into the board around the axis of rotation. And here omega, angular momentum will be in that direction. Angular momentum will be in that direction. So look at this carefully. Yeah? I'll mark it in 2 different colors. Omega there means angular momentum will be in that direction. L symbol. Torque will be acting perpendicular to this. RMG torque along the axis. Now rotating axis is here. Torque will be acting there. This is 90 degrees. So technically, torque, if I mark it, torque and angular momentum, if I look from top view, are acting perpendicular to each other. Just to make this a bit more interesting, think about an object going in a circular path. If you look at it carefully, you will have a centripetal force and a tangential velocity there. Centripetal force, tangential velocity there. In other words, tangential momentum there. Force here. Now, you know torque and force are equivalent. Angular momentum and linear momentum are equivalent. Here you can say force and momentum are perpendicular to each other. So the object will keep going in a circle. So a similar motion occurs here. Technically, the angular momentum and the torque, in between this, they will start going in a circle. In between this. So between the angular momentum and the torque, this will what keep going in a circle. Rotation motion. Just like that. Centripetal force, momentum are perpendicular to each other. Same way, equivalently, torque and angular momentum are perpendicular to each other. Why are you going in a circle here? Technically, the momentum is trying to come in the same direction as force. It can never happen because they are perpendicular. They just keep on going in circles, mathematically. Same way, we don't need too much of math, so we just get the connection. So force and momentum are perpendicular to each other. Since force and momentum are perpendicular to each other, so what happens? In between them, they keep going in a circle. So same way here, torque and angular momentum are perpendicular to each other. So in between them, they'll keep going in a circle. So from top, if I see, this will keep going in a circle. The answer is the axle will rotate about the vertical axis through A, while AB remains approximately horizontal. The correct answer is answer 3. Remember, this motion and circular motion are equivalent motion. If you remember the circular motion, you can nicely make the connection. Okay? You can nicely make the connection. Okay, no? Right. What else? There are a few questions where to think. Patterns. Think in terms of the patterns. Right. Nice question. Question 33. Question 33. Look at this carefully. Now, a grain of sand is stuck to the tire of a vehicle. A grain of sand is stuck to the tire of a vehicle. So there's a vehicle, there's a tire, there's a grain of sand. At a distance r from the center. The tire is there. At a distance r means can be anywhere. Okay? At a distance r from the center, right? So like this. The radius of the tire is capital R. So radius of tire is capital R. There you go. When the tire is rotating with constant angular speed omega, the sand grain detaches suddenly from the tire. This comes out. So there's a piece of mud, piece of sand. When the wheel is rotating, the piece of sand is coming out. Right. If the air resistance is neglected, the horizontal component of the velocity of the grain relative to the vehicle immediately after detachment could have a value between. I'll keep position A, position B, position B. So let's say the vehicle is going forward. Center here is going forward with a velocity V. And the wheel is rotating, so wheel rotation here is omega. So here you will have r omega. Here you will have r omega. Don't forget there is a velocity here as well. Don't forget there is this velocity here as well, plus v. This is something that most people forget. the velocity of the vehicle is also added to that grain of particle. Huh? That's why now check and see when you're driving, sometimes you're going behind the lorry. There is a stone stuck in the lorry. Sometimes you have double tires in between. When this rotates, quickly the stone will come and but knock on the windscreen. There will be a crack on the windscreen. Has happened many times to me. I think around 2 times to me. Sometimes the stone is very, very small, but the relative motion that it comes is very, very high because you are also traveling with a particular speed behind the vehicle. Okay? You can crack the glass. Oh, some of you all forgot this. You all forgot to think that the vehicle's velocity is also added to the particle. Okay? So next time, don't forget those. Huh? Those small things. Sometimes in experience, you will realize the vehicle's velocity also should add. Some of you all just thought R omega. But there you go. Now, if I write this, center is here. You can take it any way you want. They are in opposite direction. So I'll take here V minus R omega, particle A. Point B, here we have V plus R omega. All are at a radius R. Here velocity V rotating with omega. There you go. So what are they asking you? Horizontal component of the velocity relative to the vehicle. Velocity of A with respect to Earth. Now I'm looking from Earth. That's V minus R omega. Velocity of the car with respect to Earth. V forward. So what are they asking you? Velocity of A with respect to the car. No? So velocity of A with respect to Earth. Earth with respect to car. You can write like this. So it's a, for a MCQ, it's a very good level question. I think, nice level question. Here V minus R omega forward. Earth to car means V is traveling in the opposite direction. Bring all velocities in the same direction. V minus R omega, that was the same minus V. V cancel off. Minus R omega. Velocity of A with respect to the car, I have found. Velocity of B with respect to Earth, I'm looking from Earth, I can see V plus R omega. Velocity of B with respect to the car, I can write B to Earth, Earth to car. B to Earth, Earth to car. Here B to Earth, V plus R omega. Earth to car, V in the opposite direction. Here. R to Earth, forward means Earth to car, backward. Bring all velocities in the same direction. There you go, minus V. V cancel off, R omega. So velocity of B with respect to the car, R omega. So it's always between minus R omega and plus R omega. It's between minus R omega and plus R omega. So minus R omega plus R omega means answer is answer number 4. Yeah. So next time you're traveling by bicycle or somehow mud is coming and knocking on your face or whatever, remember with respect to the vehicle, when you are sitting, pedaling in the bicycle and going, mud is coming and now if you on a rainy day, now these days are good. You wear your banyan, white color banyan or white color t-shirt, remove the mud guard, pedal. Check and see from the head here along your back, mud particles will be there. Remember, when this is rotating, mud particles from here are what coming and knocking at you in what projectile motion. So when this rotates, mud particles here will what release themselves and what knock on your body. And they are coming with respect to you. Now when you're pedaling, you can feel the mud come and knock. That velocity is knocking you with respect to the vehicle. You are pedaling. There you go. Minus R omega plus R omega. Right. Okay, no? Right. So yeah. It's not a difficult thing, huh? Okay. Question number 34. Question number 34. Question number 34. Question number 34. So question 34. Consider the point P on the circumference of a plate with center O. So there's a plate here, somewhere here. Okay, no? Somewhere there. As shown in the figure, angle 45 made by OP with the x-axis. Angle 45 made by OP with the x-axis. OP angle 45 made with the x-axis. Okay, no? Right. At time t equal naught, plate starts from rest and around its axis with a constant angular acceleration of 4 radians per second squared. Angular acceleration 4 radians per second squared. At a time simple t, the angular displacement of the particle point P in degrees is. Interesting question. They are asking the angular displacement. What's the total angle rotated in the time t? Well, constant angular acceleration starting from rest. Yeah. Constant angular acceleration starting from rest. Now, theta equal omega naught t plus half alpha t square. Starting from rest. Alpha is given how much? 4. No? T square. Theta equals 2t square. Remember, this answer here is not in degrees, it's in radians. Rad. That's something that you should know. I mean, you should understand. Once it is in radians, then you must convert the radians into degrees. How do you convert the radians into degrees now? You all know this. You all are experts in this. This is a basic work. Pi radian equal 180 degrees. 1 radian equal 180 over pi. 2t squared radian equal 180 over pi 2t squared. That is 360 t squared over pi. The total angular displacement. Total angular displacement. Total angular displacement will be the initial angle 45 plus the angle theta rotate. That is 360 t squared over pi. See whether there is an answer like that. Yeah, there is an answer like that. No? Answer number 2. Okay. Clear. Right. So again, not difficult. Just think a bit. Take time with your experience. Don't panic cause. If you panic cause your problem. Just keep a fresh mind. Think in terms of the basic theories that you all know. Then this is not difficult. And think practically also. Okay? Try to visualize it. And if you visualize it, you have a lot of solutions will come. Okay? Right. Question number 38. Question number 38. A wheel starting from rest is allowed to roll down without slipping along an inclined plane as shown in the figure. Which of the following best represents the variation of the velocity at point P located on the perimeter of the wheel relative to the earth? Then P touches the inclined plane at T equal now. That means starting from rest. Right. It's a trick question, but not difficult for you all to solve. T equal naught, P is touching the bottom. All of you all know when feet touches the bottom, it is always at what? Always at rest. Feet touching the bottom means always the point there is at rest. Okay. Feet touching the bottom means always is at rest. Now I want you to think carefully and answer. Let's say it goes one full circle, one full revolution. Now there is a velocity here. Here, what will be the velocity? Here, what will be the velocity? Here, it will be at rest. Here, the velocity is how much? 2v. Can you remember? Rolling without slipping. Here, maybe, yes, you have started from rest. Once you come down here, there is a velocity. There, the velocity is double. Here, the velocity is 0. One full revolution. So, when particle P travels from here to here, velocity is increasing. Here to here, velocity is decreasing non-linearly, like a curve like that. Increasing, sorry, increasing, reducing. Now, if I plot it like this, just to get a small picture in your head, how the velocity will change. It will start from 0, increase and decrease to 0 again quickly in one periodic time. Now tell me, when it's coming down, the speed is increasing. The speed is increasing means quickly it's going a circle. Quickly it's going a circle means now it's traveling much more quickly, but the velocity is increasing, quickly completing the circle. Velocity is also high. So here V means here 2V, 10 means 20. Then coming down 30 means they are 60 higher. Then even higher. Time is even shorter. This time gap keeps on reducing. Here this time gap is T1. Here the time gap is T1. Here it's T2. Here it's T3. No? Right? When it's coming down, this velocity is increasing. This maximum velocity also increases. Example. When it comes here 10, let's say 10 meters per second, 10 means 20. Then after some time it becomes 15. 15 means here 30. Maximum is bigger. But it's rotating quickly. Because it's rotating quickly, the time to go a full circle will reduce. So this time will keep on reducing. Look at that and tell me which answer is correct. Gap keeps on reducing. Correctly is answer number 5. Gap keeps on reducing. Answer is answer number 5. If you just think in terms of common sense, if you just think in terms of general yours, this part you should know in terms of theory. But faster you go, it will go quickly. So time taken to go a full circle will reduce. Time taken to go full circle reduces means this time gap will keep on reducing. Yeah. Right. Because the angular acceleration is large. Because the angular acceleration will be large. Okay. Angular acceleration will be large. Right? If you look at question number 39. Question number 39. Question number 39. Variation of the angular acceleration of a wheel of a motor vehicle starting from rest with time t shown in the figure. Variation of the angular velocity omega with time is given by. Good question. Now, what have they given you? They have given you how the angular acceleration changes. Now, those days in your normal BP graph knowledge, area under acceleration time graph is giving you a change in velocity. Change in velocity. Change in velocity. So, area under angular acceleration graph will give you a change in angular velocity. Okay. Change in angular velocity. But they're telling you it's starting from rest. Okay. So, constant angular acceleration. So, they're given you larger, then smaller, then even larger. This area is bigger. I name this A1, A2, A3. A1 is bigger than A2, but A3 is bigger than everybody else. A3 is bigger than everybody else, right? So if I plot the angular velocity with time graph, all are constant accelerations. Remember, area will give you a change in area gives you delta omega, change in angular velocity. But the initial angular velocity is given as 0. Huh? Right. Okay. Carefully work. Constant angular acceleration starting from 0, constant angular velocity. Now there is angular deceleration, but this area is small enough. Area is smaller means it won't go back. It will slightly reduce. Slightly it will reduce. That's correct. But acceleration is large means gradient is large here. Right? It keeps on going what? The direction won't change, keeps going forward. This is correctly given in answer number 3. This is correctly given in answer number 3. Correctly given in answer number 3. Right. Okay. Question number 40. Question number 40. Question number 40. A child is standing at x equal minus r. So it's like an axis. Like a small axis given. So here you have circle. This side is taken as positive. This side is taken as what? Negative. One side is positive, one side is negative. Okay. No? Now when one side is positive, one side is negative, they're telling this child is standing here at minus r. So minus r the distance. Right. Using a driver motor, the merry-go-round is set to rotate in rotational motion. So there's external, somebody is providing external torque, the motor is working. Yeah. And it's rotating with constant angular velocity omega. Omega naught is constant. About a frictionless bearing. So there is no loss of energy as well. No loss of energy as well. Now if the child starts to move in the x direction along the diameter of the merry-go-round, so he's going from minus r, he's going to plus r. Minus r to plus r, he's going to go. Minus r to plus r, he's going to travel. Okay. The variation of the angular velocity omega with position x of the student is best represented by. Don't panic now, just look. So moment of inertia of merry-go-round, I'll take moment of inertia of merry-go-round. Moment of inertia of merry-go-round, I'll take as I will. Mass x. When the child is moving, there is no torque acting along the axis of rotation. If there is no torque acting along the axis of rotation, you can apply what? Law of conservation of angular momentum. So, no torque along the axis of rotation means you can apply law of conservation of angular momentum. If you can apply law of conservation of angular momentum, then this is much more easier. I omega is going to be what? A constant. I omega is going to be a constant. Right? Okay. Now they're asking you how the angular velocity will change. Now just think and tell me. When I'm coming closer to O, A to O, side is getting closer, moment of inertia will reduce, omega will increase. O to, let's say, B, O to B, moment of inertia increasing, omega reducing. But when it's here, omega naught means there is omega naught. So at A, omega naught means at B also omega naught. Is it a straight line variation or a curve variation? I omega constant. I omega constant means like non-linear. Huh? It's going to be a curve. If it's going to be a curve, it can never be zero. So your only solution is going to be, I think, answer number 2. Look at this carefully. Just this, without anything much. Minus r plus r. Here you go. Here omega naught, here omega naught. The moment you come closer, omega will increase. Maximum there at the center. Again, going away, it will decrease there. This variation means correct answer, answer number 2. This variation means correct answer is answer number 2. And guaranteed non-linear variation is non-linear. No? Non-linear variation. Okay, no? So when the child is coming from A to O, moment of inertia reduces, omega increases. When child is going from O to B, moment of inertia increases, omega reduces. At A, it's omega naught means at B also omega naught because same moment of inertia. Moment of inertia at A is equal to moment of inertia at B. Therefore, the moment of inertia same means omega naught same. Here it will be maximum. They are only maximum. So this curve is given only in answer number 2. Curve is given only in answer number 2. Right? Curve is given only in answer number 2. Okay, no? So here the main idea is they're just testing your basic knowledge. When the person is walking, how you can identify how the moment of inertia changes. When moment of inertia changes, omega will change because of our law of conservation of angular momentum. The closer you come to the axis of rotation, distribution is less. Distribution is less means moment of inertia is less. Moment of inertia is less means omega is less. The further you go away, moment of inertia increases, omega will what? Reduce. But the thing is, at A and at B, moment of inertia are equal. If moment of inertia are equal, omegas are also what? Okay, no? Right. Question 41. Question 41. A uniform disk of mass M, and radius r rolls without slipping initially along a horizontal surface. The disk has a linear velocity v on the horizontal surface. The moment of inertia of the disk above the axis through its center and normal to plane of the disk is half mr squared. What is the maximum height to which the center of the mass of the disk can climb? What is the maximum height that it can climb? Right. So you are applying apply law of conservation of energy. It's going to go like this too. Right. So we can take this as the GP equals 0 line. Once it reaches here, let's say it comes to rest. Center of gravity. Yeah. This is your H. So don't forget there is a velocity V and don't forget there is a omega there as well. Rolling without slipping, no? V equal R omega. Rolling. The rolling condition is V equal R omega. Don't forget. Right. So what are they asking you? They're asking the height. Okay. Remember, rolling without slipping, there is going to be friction. There will be friction. You can't say no friction. Frictionless surfaces, you can't roll. But there is no work done by static friction. The bottommost point is at rest. When the bottommost point is at rest, static friction will act. Static friction does not do any work. So we can apply energy. Total energy at A equals total energy at B. Total energy at A is kinetic, half mv squared, half I omega squared. Total energy at B is just gravitational potential energy, mgh. Now you can simplify this. You can simplify this. Half m, they want in terms of v. Half m v squared. Moment of inertia is mr squared over 2. Omega is v over r whole thing squared. That is equal to mgh. That is equal to mgh. So if you simplify this carefully, half mv squared, mv squared over 4, mgh. Half and quarter, 3/4, mgh. Mm cancel. Cancel off. So what is your h? 3v squared over 4g. Do you have an answer like that? Yes. It's a matter of you all taking time to think and solve the problem. Okay? All it takes is a bit of thinking and a bit of patience. Remember, when you're doing science, you need a lot of patience. There is no shortcuts to success, no fast tracks to success. It is a process that you have to follow smartly. Yeah. Right. Question number 44. Question number 44. A uniform solid wheel rolls along a flat surface with a uniform velocity v without slipping as shown in the figure. P is a point located on the circumference of the wheel. Location of point P at t equal naught is shown. Variation of the horizontal component of the velocity Vx of the point P with respect to the surface. With the time T is best represented by. Interesting. Remember, rolling means bottommost point is always at rest. Here velocity v means highest point, always velocity 2v. Just like we did in the earlier question. From 0 to 2v, there is going to be a non-linear increase. 2v to 0, there will be a non-linear decrease. But since it's going on a horizontal surface, it's going horizontally. Since it's going horizontally, the time taken will be the same. Now, earlier one, it was coming down the plane. When it was coming down the plane, the velocity is increasing. But here, velocity is what? Same. You might say, so there is friction, it will slow down. No, it has friction. But it's static friction. Static friction will not do any work. It will slow down. So this will increase, decrease, increase, decrease. Velocity is 2v. Horizontal component. Do you have an answer like that? Yes. You have an answer like that. Answer is answer number 1. Answer is answer number 1. So you can see just small, simple variation. And when you apply the theory, you have your answer. Okay? When you apply the theory, you have the answer. Right. So you are sending send some questions also. Those also I'll discuss. Yeah. Those also I'll discuss. Right. So keep sending your question, which is good. Right. Now, some of the questions that you have sent. Right. There is this. Okay. Fluids, hydrostatics. Question number 51. Hydrostatics, question number 51. There you go. A thin walled cylindrical vessel is floating in a lake at a time t equal naught. A small hole is made at the bottom of the vessel of water and is allowed to flow into the vessel at a constant rate. So that the vessel immerses with constant velocity. It starts sinking. If H1 is the difference in heights of the water levels inside and outside, which of the following curves best represent the variation of H1 and H2 until the vessel is fully immersed? So here you go. Outside there is water, inside here they are talking about a level here H1 and they are talking about a height difference there H2. Now we have done a similar question. We have done a similar question, question 33. All of you all know the difference in height will always remain constant. The difference in the liquid level, the difference in the height will always remain constant. So best thing I think I should do 33 again just to remind you. 33 I'll do it again just to remind you all. So this MCQ is much more easier. Read below. Question 33. A cylindrical metallic vessel having thin walls of height 4h. The height here is 4h. Height here is 4h. Here you go. This height is simple h. This height is 2h. This height is 2h. Now what's going to happen? It's still floating. Upward forces, balances, downward forces. Upward force will be upthrust. Upward force will be upthrust. So weight of the vessel is there. Weight of the vessel is there. Weight of this water is there. I take the area as A. H rho WG. Upthrust is there. A 2H rho WG. Simplify this. AH rho WG, that is equal to M1G. Right? Now what's going to happen? The water starts coming in. Water starts coming in. Maximum level that water can come, it's on the verge of sinking. That's the height. That's the question they're asking you. It's that. The weight of the boat is separate. Here, completely submerged 4H. Completely submerged 4H. Upward forces, balances, downward forces. Upward force is upthrust. A 4H rho WG. Downward force is the weight M1G plus. A H dash rho WG. Be careful now. 4AH rho WG. M1G is AH rho WG. AH dash rho WG. Simplify. 3AH rho WG AH dash rho WG. If you simplify this, rho WG, AA cancel off, H dash equals 3H. Now look at this carefully. Yeah? These on the verge of sinking. What is the difference in the liquid level here? Now this is 3H. No? What is the difference in the liquid level here? As long as the difference in the liquid level between the outer surface and the inner surface is constant, sinking will not take place. But now after this, when it starts increasing, it will start to reduce, it will start to sink. So when you're on a boat or whatever, water is coming inside, if you can keep the outer level and the inner water level height constant. Have you seen cartoons when water is coming in, one flow start putting water out? Well, that's the scientific idea behind that. Trying to keep the outer water level, inner water level, what? Height difference same. Huh? He'll just apply the sail, start to see. The fellow keeps on putting water out, he gets tired. Then what happens? The fellow will sink, keep the ship. Okay. So here, as long as this difference, outer level, inner level difference is constant, sinking will not take place. But beyond that, sinking will take place. Okay. When the difference starts to reduce beyond that, guaranteed, sinking will take place. Right. We have that idea. So now come back to question number 51. So as long as H1 is constant, sinking will not take place. As long as H1 is constant. So non-constant graphs you can remove. Third, fourth, you can guaranteed remove. Third, fourth, you can remove. Huh? So when, what can you say about this outer height? There also they asking that question, outer height. Now 4H, 2H, this is 2H. Now outer height is there, now 0. Outer height will keep on reducing. No? Outer height will keep on reducing. But the difference here, inner height should be constant. Inner height should be constant, H1. H1 constant. Okay. H1 constant. Outer height keeps on reducing. Outer height keeps on reducing. So even when the outer height is actually 0 at this state, when the outer height is 0, still H1 can be what? Constant. When outer height is 0, still H1 can be constant according to this picture. And then suddenly what sinking will take? Quickly, the reduction will take place. Quickly, the reduction will take place. Okay. So this question, very good question. But you have to think in terms of the earlier question that you have done, no? See how the connection is made? You have to think in terms of the earlier question that you have done. So if you think in terms of the earlier question that you have done, correct. So that's the beauty of this question. No? That's the beauty of this question. So from this, I can conclude that question 51, when H1 becomes 0 also, when H1 becomes 0, sorry, H2 becomes 0, H1 height is still what? Difference is the same. Difference is the same. After that, quick what reduction will take place. Correct answer is answer number 2 for 51. You can see how earlier questions will help you what analyze. Okay. Right. So send in more questions. We'll keep discussing like this and going. I hope you all enjoy this as well. If you can't join exactly at the correct time, but still make sure you watch the what you call video as well if you're on YouTube, and make sure that you learn from it. Take time to analyze it, take time to learn, and it's helpful for you to get good results as well. Well, till next time. See you all next week at the same time. Good night. Stay safe.